In the quiet depths of our galaxy, a star named LB-1 moves in a way that shouldn't be possible. Astronomers believe something invisible, maybe a silent black hole, is pulling the strings. Tonight we'll explore the mystery hidden within its light. If you enjoy uncovering cosmic secrets, please subscribe and share, and tell us in the comments, do you think LB-1 really hides a black hole? Thank you for watching. Now let's begin. The line of sight to LB-1 lies within the constellation Gemini, a region that sits north of the Milky Way's midplane, yet still brushes a broad field of galactic stars' dust and faint nebulae. In clear conditions, the area presents as a quiet scatter of points against a dark background, with no bright knots of emission to dominate the view. Along this direction, the arm of the galaxy that contains the Sun, sometimes called the local arm, gives way to more distant lanes, where the star density rises and falls gently with latitude. Interstellar dust made of tiny grains of carbonaceous and silicate material thins the light in slow measure so that stars appear a touch redder and dimmer than they would in a dust-free sightline. The reddening is not dramatic here. It works like a soft filter rather than a curtain, allowing the underlying stellar field to remain legible. Gas clouds, mostly hydrogen, with traces of helium and heavier elements, thread the scene in long, low, contrast filaments that reflect or scatter starlight so weakly that they barely disturb the darkness. Against this restrained canvas, LB-1 holds a modest place, neither a beacon nor a hidden ember, but a stable point whose steadiness rewards careful attention. The sky location in Gemini sets a simple geometric context. The constellation's recognizable pattern, anchored by the bright stars Castor and Pollux, frames a swathe where the Milky Way's band is subdued, compared to the crowded richness of constellations closer to the galactic center. The absence of glaring star clusters or intense emission regions helps. The field is not empty, but it is calm. In such a field, a star of moderate brightness can be tracked without confusion from overlapping halos or complex background structure. The line of sight angles outward from the center of the galaxy toward its outer spiral structure, so the cumulative column of dust and gas grows more slowly with distance than it would toward the center. This geometry leaves room for relatively clear windows where photometry and spectroscopy face fewer complications from foreground haze. The thin veil that remains still matters, because even a small amount of extinction alters color and brightness measurements, and small alterations accumulate in any chain of inference. In practical observing terms, the field's calm favors stable seeing precise tracking and clean background subtraction. Long exposures gather a rich speckle of faint stars that form a statistical backdrop. The backdrop is useful because it supplies reference points for astrometry and calibration, and it remains non-intrusive because no single neighbor star overwhelms the frame. When the atmosphere steadies and a telescope's optics rest at equilibrium, the star images in this region take on near-circular profiles, with only mild scatter easing the extraction of accurate positions and fluxes. LB-1's placement in this orderly patch of sky allows it to be measured in multiple bands without severe contamination by diffuse emission or bleed from brighter sources. The galactic environment along the sightline also shapes expectations about intervening material. Dust maps built from far infrared emission and stellar reddening show gradients that run slowly across Gemini with small knots, where dense clouds hover but do not dominate. The knots are offset enough from LB-1's position that their influence, while not zero, reads as gentle rather than abrupt. Scattering from dust grains produces a faint diffuse glow at very low surface brightness, but this glow sits below the thresholds that trouble typical stellar observations. Neutral hydrogen surveys register long-layered sheets that slice across the field with velocities that shift gradually with longitude and latitude tracing the galaxy's rotation. These sheets contribute to absorption features in the ultraviolet and radio, yet at the optical wavelengths used to classify stars, the main effect is the aggregate dimming and reddening already noted. Magnetic fields thread the gas and dust, organizing some of the filaments into softly aligned structures. Polarization measurements of starlight where available reflect this alignment in small degrees, nudging the light's orientation by a measurable but mild amount. Such effects hint at the subtle complexity of the medium without altering the basic appearance of the field. The stellar population projected behind and in front of LB-1 spans a wide range of ages and temperatures. Cooler dwarf stars dominate the counts by sheer number, while a smattering of hotter, more luminous stars mark the spiral structure like waypoints. The density of these waypoints is informative. It rises where a spiral arm crosses the view and falls between arms, creating a loose rhythm of brightness that recedes with distance. Star clusters are present, but they tend to be diffuse and older. In this part of the sky, their brightest members not so brilliant as to wash the scene. Farther out, the disk thins and the halo populations begin to contribute a sparse scatter of ancient stars whose motions point out of the plane. This layered depth offers perspective. LB-1 does not sit in isolation, but along a corridor of the disk where the Milky Way's structure can be sensed in the statistics of the background. The seasonal placement of Gemini in the night sky means that many observatories catch this field under long, cool nights when the air is often dry and stable. Dry air reduces atmospheric absorption in the red and near-infrared, improving the fidelity of measurements where interstellar reddening pushes starlight. The ecliptic passes not too far away, but planetary glare rarely intrudes upon the specific coordinates used for repeated monitoring. This practical convenience has helped build a steady archive of images and spectra that preserve the field's character across instruments and years. The alignment of Earth's rotation and the target's declination yields comfortable tracks across the meridian, limiting differential refraction and smearing at high air mass. Calibrations taken on the same nights, using standard stars with well-measured colors, translate the counts on detectors into physical fluxes and colors that can be compared across epochs. Within this stable observational frame, LB-1 appears as a blue-white point, with a brightness that makes it accessible to medium-sized telescopes, while remaining well within the dynamic range of larger instruments. The blue-white hue signals a hot photosphere, and the steadiness of the point spread function in this field means that small departures from a symmetric profile can be noticed if they occur. Photometric measurements taken through filters that sample the blue and visual parts of the spectrum show color indices that fall where hot stars typically land after modest reddening by dust. Nothing in the wide-field image announces a dramatic environment. There are no sharp rims of ionized gas, no dust pillars etched by bright newborn stars, no arcs carved by strong stellar winds. The quietness is useful. It means that light arriving from LB-1 travels through space that adds little of its own structure to the signal. This does not remove the need for care. Even gentle extinction must be accounted for, and even a calm field can hide faint gradients. But the sky here cooperates with patient work. The coordinates in Gemini give a consistent stage upon which repeated measurements can be made and compared. With each clear night, the same pattern of background points returns, the same dim lanes of dust soften the view in much the same way, and the same slow geometry of the outer Milky Way supplies depth without confusion. LB-1 sits within this order as a reliable source whose sky context is steady enough to anchor precise studies. The field neither distracts nor deceives, it invites close looking. In this established setting, the star's light reaches instruments with only the usual interstellar and atmospheric signatures layered upon it, allowing careful measurements to begin from a stable baseline that needs only modest corrections for dust and air. The line of sight through Gemini thus offers a measured clarity, a scene quiet enough to carry the signal from a single star cleanly and complex enough to remind that every ray has crossed a galaxy filled with dust, gas, and other stars before it enters a waiting telescope. Spectroscopic surveys of the northern sky proceed with a quiet regularity that suits long projects. Wide fields are tiled again and again, and instruments place small apertures upon stars that meet colour and brightness criteria drawn from all sky catalogues. Hot stars rise within such lists because their blue-weighted light stands out even after a modest measure of interstellar reddening. In this routine stream, a moderately bright target in Gemini enters the schedule as one among many hot star candidates flagged by colours that suggest a surface far warmer than the Sun, and by a steadiness that promises clean measurements. The observing plan pairs short integrations for bright objects with longer exposures for faint ones. But either way, the goal is the same: to obtain spectra that show how intensity varies with wavelength so that each star's type and motion can be measured. Raw frames record the light of hundreds of objects at once, together with calibration lamps and blank sky. Pipelines subtract bias, divide by flat fields, remove scattered light, and trace the little rainbows into one-dimensional spectra. The wavelength scale is anchored to comparison lamps and night sky lines, and then each spectrum is shifted into a standard frame so that absorption and emission features can be compared across nights. Most hot stars observed in this way yield familiar patterns. Broad hydrogen lines curve across the plots, with smooth wings that tell of high temperature and high pressure in the photosphere. Helium lines add their marks, and weak traces of heavier elements step in where the signal allows. The classification proceeds efficiently, filling tables with spectral types and luminosity classes that can later be matched to distances, colours, and motions from astrometric surveys. The target that will become LB-1 in common usage follows this path at first. Its spectrum looks like that of a hot blue-white star. The hydrogen lines are strong. The helium features appear at the expected places. The shape of the lines hints at rapid rotation, because rotation spreads the light from each patch of the surface across a range of velocities, which blurs a sharp notch into a wide trough. The line cores are shallow, and the wings are smooth, exactly the sort of profile that classifiers know well. That would be the end of the story for many entries, but surveys do not observe once only. Repeat passes collect second and third spectra across months and years, both to increase signal and to search for changes. When the same target is revisited, the spectra are placed side by side, and any shift in the position of the lines is measured as a radial velocity. Small drifts are common because stars move within the galaxy, and instrumental 0 points wander by tiny amounts that careful calibration corrals. What draws attention are consistent periodic shifts that suggest orbital motion or unusual features that do not match the expectations for a solitary, rapidly rotating hot star. In this case, a familiar sign of a disk appears emission in the deep red hydrogen line that rises above the continuum rather than dipping below it. Emission in hot stars is often a signature of a thin rotating gas disk fed by the star's rapid spin. Such a disk is called a decretion disk, and it throws a characteristic double-peaked shape into the red hydrogen line when the disk is seen at an angle with one peak from gas rotating toward the observer and one from gas rotating away. The survey spectra show a variant of this theme. The emission stands clear and the photospheric absorption lines move slightly between visits. The combination urges caution and curiosity. A rapidly rotating star can carry a disk and also belong to a pair. If so, the absorption lines from the star's surface will slide to and fro with the orbit, while parts of the disk can appear relatively steady if the gas forms an extended ring whose internal motions dominate over any slow drift of the center of mass. The logs mark the target for closer scrutiny. Flags are attached that ask for more epochs to improve the sampling of phase, the fraction of the orbit covered by the observations. The star's brightness, neither too bright for the detectors nor too faint for clean line shapes, helps. It can be observed with medium-sized telescopes that have flexible schedules, so nights lost to weather can be made up, and windows of good seeing can be used to gather higher quality data. The coordinate in Gemini further helps because the field rides high for a comfortable stretch of the night during a season when many observatories enjoy steady air. With each new spectrum, the pattern grows clearer. The absorption lines tied to the hot star's surface slide back and forth. The emission in the red hydrogen line varies in shape but does not march in lockstep with the absorption features. This differential behavior is not exotic on its own, but it is informative. It suggests that more than one region of gas contributes to the light within the aperture. The survey team increases the cadence to trace the timing of the shifts and to test whether the velocity curve repeats with a consistent period. Photometry joins the effort. Even a simple sequence of brightness measurements taken through broad filters can catch changes caused by a disk that thickens and thins, or by subtle eclipses if the orbital plane happens to tilt near the line of sight. In this case, the brightness stays relatively stable within the precision of routine monitoring, another hint that any orbit is wide enough to avoid deep mutual shadows. Archival searches extend the baseline backward. Older photographic plates and digital imaging surveys reveal that the target has not erupted or faded dramatically in recent decades. The steadiness supports the idea of a mature hot star with a long-lived disk, rather than a newborn object or a dramatic outburst. Meanwhile, the pipeline refines radial velocities by cross-correlating the spectrum with templates of stars that share the same basic properties. Cross-correlation is a mathematical comparison that yields the shift that best aligns the absorption features, and from that shift a velocity is derived. By repeating this across many lines and many epochs, a velocity curve emerges. It shows a slow, smooth oscillation measured in many tens of days, a clue that points away from a very tight orbit and toward a wide pair. The survey collaborators consider the possibilities open at this stage. A rapidly rotating hot star can be spun up by past mass transfer from a companion which can leave surrounding gas in a disk. A companion can be another star whose light is faint in the blue, and thus hard to see, or a compact remnant that contributes little or no direct optical light. Distinguishing between these options requires more than survey cadence. It calls for deeper spectra with higher resolution and for attention to the fine structure of the emission profiles that can betray the motion and temperature of the gas. The survey's role is to mark the field, define the repeatability of the velocities, and demonstrate that the target is worth the time of more specialized instruments. By now the star has moved from a routine catalogue entry to an ongoing project. It stands out not because it flares or dims, but because its spectra carry two voices at once: the broad moving absorption of a fast photosphere and the persistent glow of gas that encircles or neighbours it. The data quality is high enough to avoid confusion from overlapping stars, the seasonal coverage is long enough to outline a period, and the archival sources help ensure that the baseline is secure. All of these practical virtues come from the survey approach itself, large samples that can be revisited, uniform processing that keeps measurements consistent, and a design that favors hot stars whose light carries clean fingerprints. Within that framework, LB-1 becomes a curiosity worthy of follow-up, not because a single spectrum is strange, but because the ensemble of spectra fits a coherent but non-trivial picture. The survey has done its work. It has gathered enough light to reveal motion enough epochs to suggest a clock, and enough context to show that the target sits in a calm field where interpretation will not be swamped by confusion. From a simple color cut and brightness threshold has come a candidate whose layered spectrum invites patient targeted observations, and whose place in the sky allows those observations to continue until the pattern is traced with confidence. Photometry begins with the simple act of measuring how bright a star appears from Earth, and then asking how that brightness changes with wavelength, because starlight carries different amounts of energy in blue and red bands depending on temperature, dust, and distance. Instruments collect photons through standard filters that isolate broad slices of the spectrum, commonly a blue band and a visual band that is slightly redder than blue, and sometimes additional near-infrared bands. The resulting counts are turned into magnitudes, a historical brightness scale, in which a smaller magnitude corresponds to a brighter source using standard stars observed on the same night to calibrate the 0 point and the sensitivity of the detector. The difference between the blue magnitude and the visual magnitude is the color index, a single number that compresses the shape of the spectrum into an easy measure of color. Hotter stars emit more power at shorter wavelengths, so a truly unreddened hot star presents a negative or small color index, meaning it is bluer than the comparison scale. Real sightlines through the Milky Way are not empty, so interstellar dust makes itself known by dimming and reddening the light in a wavelength-dependent way, an effect called extinction. Dust grains made mostly of silicates and carbon-rich material with sizes comparable to the wavelengths of visible light scatter and absorb blue photons more efficiently than red photons, so the star appears fainter and redder than it would in a dust-free vacuum. The amount of extinction depends on the total column of dust and on the distribution of grain sizes along the path. Within Gemini, the dust column toward LB-1 is moderate, not negligible, and not severe, which means extinction corrections matter but do not dominate. On a clear night, a series of measurements through blue and visual filters yields a stable color index for LB-1 that is slightly larger than the value expected for an unreddened hot star, a quiet sign that dust is at work. To separate intrinsic color from dust, reddening observers combine the color index with a spectral type estimate from spectroscopy. Spectral type gives an intrinsic or natural color, expected for a star of a given temperature and gravity if seen without dust. The difference between the observed color and the intrinsic color is the color excess, which is a measure of reddening. With a reasonable estimate of the color excess, an extinction law converts reddening into the total amount of dimming at visual wavelengths. An extinction law is an empirical relation that tells how dust affects different wavelengths, often summarized by a parameter that describes the average grain size distribution along the line of sight. In the direction of LB-1, standard extinction laws that apply to diffuse interstellar medium tend to fit, so the corrections follow established practice. The next step is to fold these corrections into a distance estimate. If a star's absolute magnitude, which is the brightness it would have at a standard distance, is known from its spectral classification and luminosity class, then the observed magnitude, once corrected for extinction, can be translated into a distance. Each piece of this chain carries uncertainty. A small shift in color index because of calibration errors, a small mismatch in the intrinsic color, Because the star rotates rapidly and alters its apparent temperature at the equator versus the pole, or a small change in the assumed extinction law, all ripple into the distance. Rapid rotation matters for LB-1 because rotation flattens the star slightly and can make the equator cooler and dimmer than the poles, an effect called gravity darkening. When a star is viewed at some inclination, gravity darkening tilts the flux distribution in subtle ways that influence broad band colors. Disk emission can also add continuum light that fills in absorption lines and nudges colors. To guard against these effects, observers check for consistency across several filters and look for color changes with time. The measurements of LB-1 in blue visual and near-infrared bands tend to be steady within small errors over many nights, which supports the idea that any disk contribution to the continuum is modest at the epochs observed. Atmospheric effects must also be considered and removed. Earth's atmosphere absorbs more blue light when a target is observed at a low elevation, and even at high elevation, the transparency can drift across a night as water vapor and aerosols change. Standard practice observes multiple comparison stars with well-known magnitudes over a range of air masses to solve for the atmospheric extinction coefficient and correct the target's counts. In a field like Gemini, where there are many stable, moderately bright stars in the same frame, differential photometry can be performed. Differential photometry compares the target's flux to fluxes of comparison stars without converting to an absolute scale at each exposure, which cancels much of the atmospheric variability. Applied to LB-1, the technique shows that short-term fluctuations are small, consistent with a stable photosphere and a disk that does not flare dramatically on our timescales. The combined photometric picture is a star whose apparent blue-white color reddened slightly by dust, and whose brightness dimmed modestly by the same dust match the expectations for a hot star at a distance in the outer part of the galactic disk. The precision is high enough to place LB-1 on a color magnitude diagram alongside standard sequences. On that diagram, a main sequence star sits in a well-defined band that runs from red and faint to blue and bright. LB-1 falls on the blue side of the band as expected, though the exact vertical placement depends on the extinction correction and on whether disk light contributes to the continuum in the chosen bands. The near-infrared photometry adds an important cross-check because dust dimming is smaller at longer wavelengths, and because emission from a thin cool disk can raise the infrared flux. Modest excess in the near-infrared compared to purely photospheric models is often a disk signature in rapidly rotating hot stars. For LB-1, any such excess is measured to be small, in line with a thin, low-density disk at the epoch sampled. Over months and years, repeated photometry tests for periodic signals that might come from ellipsoidal variations, where tidal forces make a star slightly elongated and thus slightly brighter when the long axis points toward Earth, or from shallow eclipses if the orbital plane is near edge-on. In the data collected so far, no deep repeating drops appear, and any sinusoidal variation remains low amplitude, which argues for an orbit that does not produce strong geometric effects in broadband light. The absence of strong photometric modulation does not argue against binarity. Rather, it suggests an orbit with moderate inclination and separation, where radial velocities carry more information than light curves. With the color index and extinction in hand, a bolometric correction can be applied to estimate the total energy output across all wavelengths. A bolometric correction accounts for the fact that hot stars radiate much of their power in ultraviolet light that is not recorded by visual band filters. The correction depends on temperature and gravity, again linking back to spectral classification. The resulting luminosity estimate combined with the distance provides a coarse check on the star's radius when simple models of stellar structure are invoked. Rapid rotation complicates this inversion, but even with that caveat, the derived radius and temperature fall in the range expected of a hot early type star, which supports the spectroscopic classification. The consistency among blue visual and near-infrared bands, the moderate and well-behaved dust, reddening along the line of sight, and the lack of large amplitude variability together mark LB-1 as a clean photometric target. It is bright enough to obtain high signal measurements with modest telescopes, yet not so bright that detector nonlinearity threatens precision. It is located in a field rich in comparison stars which supports robust differential techniques. It sits behind a dust column that is strong enough to teach the necessity of extinction corrections, yet light enough that the corrections do not explode in uncertainty. In this context, the light that reaches Earth provides a reliable starting point for deeper inquiry. The colors anchor estimates of temperature and energy distribution. The magnitudes corrected for dust constrain distance when combined with a spectral type. The time series of fluxes places limits on short-term changes that might otherwise confuse interpretation. Photometry therefore supplies a foundation that is simple in principle and careful in practice. Measure the light correct for the air, and the dust compare to standards repeat across seasons, and assemble a steadied picture of what the star looks like from Earth, before moving on to pass the finer fingerprints embedded in its spectrum. Starlight spread into a spectrum becomes a map of atoms and conditions, and for a hot blue-white star the map begins with hydrogen lines that are strong and broad. Hydrogen in a stellar photosphere absorbs light at specific wavelengths, when electrons step between allowed energy levels, and the set of transitions visible in the optical is called the Balmer series. In a hot star, the Balmer lines are prominent, because the photosphere is warm enough to lift a significant fraction of hydrogen atoms into the first excited state, which is the starting point for those optical transitions. Each line has a core where absorption is deepest, and wings where the opacity falls off more gradually with distance from the line center. The width of the wings reflects the pressure and motions in the layer where the light forms. Higher pressure broadens the lines through collisions between particles. A process called pressure broadening and random thermal motions add their own blur through the Doppler effect. Rotation adds yet another contribution by smearing the light from different parts of the stellar disk across a range of velocities. In LB-1, the Balmer lines present with smooth extended wings and shallow cores, a hallmark of a hot, rapidly rotating photosphere. Helium lines step in alongside hydrogen and help refine the classification. Neutral helium shows several strong features in the blue, while singly ionized helium marks even hotter conditions, and tends to appear in early type stars on the very blue edge of the main sequence. The relative depth of neutral and ionized helium lines, together with the strength and shape of the hydrogen series, narrows the temperature estimate and thus the spectral subtype. The classification scheme for hot stars rests on calibrated sequences of spectra, arranged by temperature and luminosity class, and observers match the target's patterns against those sequences to find the best fit. Luminosity class depends on surface gravity, which influences line wings and subtle blends, so the final label reflects both heat and pressure. When the photospheric absorption features are considered in a frame where the star's bulk motion is removed, they are said to be at rest, meaning there is no net shift of the line centers relative to their laboratory wavelengths. This rest frame is a useful construct because it allows line shapes to be compared directly across epochs without the distraction of orbital shifts. To reach that frame, observers measure the apparent radial velocity by cross-correlating the observed spectrum with the template, and then remove that velocity from the data, leaving the intrinsic profile shapes that arise from physics in the photosphere and immediate surroundings. The hydrogen lines in LB-1 once placed in this rest frame reveal symmetric wings consistent with a high rotation rate. Rotational broadening spreads the profile because the limb of the star rotating toward the observer adds a blue shifted component, while the opposite limb adds a red shifted one, and the sum over the disk produces a flattened core. The amount of broadening yields a projected rotation speed which is the true equatorial speed, multiplied by the sine of the inclination angle between the rotation axis and the line of sight. In many rapidly rotating hot stars, this projected speed is hundreds of kilometers per second, and LB-1's line shapes fall within that regime. Gravity darkening complicates the interpretation by making the equator cooler and dimmer than the poles, which weights the rotational average away from the fastest moving zones. But careful modelling can account for that effect when necessary. Metal lines, a term astronomers use for features due to elements heavier than helium, appear weaker in hot stars because many atoms are ionized to states that do not produce strong optical transitions. Even so, sets of lines from elements such as oxygen, silicon, and magnesium leave measurable marks in high-quality spectra. Their presence and relative strength carry information about the chemical composition and about microturbulence, a small-scale velocity field introduced in the photosphere to account for non-thermal broadening. In LB-1, these lines are delicate and partially blurred by rotation, but they remain useful in cross-correlation and in checking for subtle changes that might betray contamination from a companion. The continuum, the smooth baseline of the spectrum between lines, rises toward the blue for a hot star, and its slope helps confirm the temperature after accounting for interstellar reddening. Across the deep red, the hydrogen line at the long wavelength end of the Balmer series becomes a special case, because it often shows emission in stars with disks. A thin, rotating disk of ionized gas can produce a double-peaked emission profile, whose separation reflects the rotation speed of the gas where most of the light is formed. When the stellar spectrum is shifted to its rest frame, this emission can appear displaced, if the disk does not share exactly the same velocity field as the photosphere at a given moment, or if asymmetric structures orbit within the disk. In LB-1, the red hydrogen line shows such emission superposed on the broad absorption, and the detailed shape of the emission changes from epoch to epoch. These changes are not random. They map the dynamics of the disk and offer a tracer of the geometry when interpreted with models of Keplerian rotation and radiative transfer. Spectral classification proceeds by comparing the entire pattern, not a single feature. And for hot stars with disks, the goal is to isolate the photospheric indicators from circumstellar additions. This separation benefits from high-resolution spectroscopy, because narrow interstellar lines such as those of calcium in the blue can be used to refine the wavelength calibration and to estimate the column of material along the line of sight. Interstellar sodium lines in the yellow carry similar information and can reveal multiple clouds at different velocities. These interstellar features are narrow and do not vary with time, which makes them stable markers against which instrumental drifts can be checked. In LB-1, the interstellar lines are present at modest depth consistent with a dust column that reddens but does not obscure the star. The classification after this careful accounting places the photosphere among early type stars with broad rotation, dominated hydrogen lines, neutral helium present, and metal lines weak. The luminosity class aligns with a main sequence, or slightly evolved star, where surface gravity remains high enough to keep pressure broadening significant. The exact subclass carries formal uncertainties because rotation and disk effects tug on the same line shapes that define the scheme. To quantify how well the template matches the data, observers sometimes compute a chi-squared measure across selected wavelength windows that avoid emission, and telluric bands, the latter being absorption from molecules in Earth's atmosphere, telluric correction removes the most intrusive of these bands by dividing the target spectrum by that of a standard star observed at similar air mass, but residuals remain and must be avoided in precise work. Once the classification stabilizes, it becomes a foundation for later steps. Temperature and gravity inferred from the spectral type feed into estimates of radius and luminosity when combined with distance and extinction. The projected rotation speed guides expectations for disk formation, because higher rotation pushes the photosphere closer to shedding material at the equator. The presence and behavior of the red hydrogen emission set a context for how gas flows around the star, whether as a thin ring, a more extended disk, or a structure with spiral density waves. In repeated spectra, observers also examine the small asymmetries in the cores of hydrogen and helium lines, which can signal non-radial pulsations, surface spots, or contamination by a companion's faint lines. In LB-1, the dominant story in the rest frame remains the combination of broad symmetric photospheric absorption and a variable double-peaked red emission line. The simplicity of the photospheric pattern supports a clean temperature estimate. The stability of helium line ratios across epochs argues for a steady photosphere, while the disk emission reminds that circumstellar gas adds a separate layer of physics. Together, these lines at rest relative to the star's bulk motion provide the fingerprints needed to anchor models. They do not yet speak to orbital motion or to the nature of any companion. That requires tracing how the entire pattern shifts with time. But as a snapshot, the spectrum in the rest frame shows a hot, rapidly rotating star with a thin, rotating gas structure that glows in the red, a combination that fits naturally within the class of rapidly spinning hot stars known for their disks. This is the starting point for disentangling motions and inferring masses, because only when the fingerprints are understood at rest can their shifts be measured with confidence. A rapidly rotating hot star can shed gas from its equator and build a thin, cool disk that orbits in nearly circular paths, and the clearest optical sign of such a disk is emission in the deep red hydrogen line. In a rotating disk, the gas on the side moving toward Earth imprints a blue shifted peak, while the gas on the far side imprints a red shifted peak, and the separation between those peaks reflects the orbital speed where most of the photons form. When the disk is viewed at a low angle, the two peaks blend until they nearly merge, while at higher inclinations they stand apart with a central dip. The photosphere of the star still contributes broad absorption, so the full profile is often emission that fills or even rises above an absorption trough. In LB-1, the profile shows this composite shape with a double-peaked emission embedded in broad absorption and a central valley whose depth varies with time. Variations in the relative height of the blue and red peaks, a pattern called V/R variability, arise when the disk density is not perfectly symmetric. A one-armed spiral density wave can precess slowly in the disk and alternately enhance one side and then the other, producing a cycle in which the blue peak dominates, and then the red peak dominates on timescales longer than the orbital period near the star. The presence of such V/R changes in LB-1, coupled with only mild changes in total brightness points, to a disk that rearranges its internal structure without large swings in its overall mass. The emission strength measured by the equivalent width of the red hydrogen line tracks the disk's content and temperature near the region where the line forms. When the equivalent width grows, the disk has likely become denser or more extended. When it shrinks, the disk has faded or contracted. In LB-1, the equivalent width varies within a restrained range consistent with a thin disk that persists but does not erupt. The broad wings of the emission fall off in a way that indicates the fastest moving gas lies close to the star, as expected for rotation governed by gravity. Changes in the peak separation offer an estimate of the characteristic radius of the line-forming region, because faster rotation implies a smaller radius. Across epochs for LB-1, the peak separation shifts modestly, hinting that the effective line-forming radius breathes with the disk's density. Additional hydrogen lines in the near-infrared, such as those in the Passion and Brackett series, often glow in B-star disks and provide cross-checks on density and temperature at different radii. When present at low to moderate strength, they support a picture of a disk that is optically thin in the continuum and moderately thick in selected lines. LB-1's near-infrared photometry shows only a small excess over a pure photosphere, a sign that the continuum from the disk is weak. This aligns with the restrained emission in the optical, and the absence of strong color changes with time. Polarization adds a geometric constraint because free electrons in a flattened disk scatter starlight more efficiently in some directions than in others, imprinting a small net polarization whose angle indicates the orientation of the disk on the sky and whose degree rises with both inclination and electron column density. Modest polarization is expected for a thin disk seen at moderate tilt. Where measured for LB-1, the polarization behaves in this modest regime and shows little rapid variation, which reinforces the picture of a settled low-density structure rather than a thick, clumpy outflow. High-resolution spectra reveal further subtleties in the emission shape. The central dip can sometimes plunge below the continuum to form a narrow absorption feature when the line of sight crosses cooler, slower gas in the disk midplane, a signature often called a shell profile. Shell features indicate a higher inclination and a cool, dense equatorial layer. LB-1's profiles tend toward filled absorption with two peaks and a shallow central valley rather than deep shell absorption, suggesting the line of sight does not skim the plane closely. Superposed on the red hydrogen line, weak metallic emission or absorption from the disk can appear, but in a thin disk these features are faint and hard to isolate against the broad stellar lines. The disk itself is fed by the star's near-critical rotation and by episodic mass loss events. Gravity darkening makes the equator cooler and less bound, and small disturbances can lift gas into orbit where viscosity spreads it outward. In the viscous decretion disk model, gas injected near the star drifts outward under the action of turbulent stresses that transport angular momentum. The surface density profile then follows a power law, and the temperature declines with radius as the disk cools by radiation. The width and symmetry of the emission peaks their separation, and the overall line strength fix combinations of the viscosity parameter, the injection rate, and the inclination. No single spectrum pins all these quantities, but time series constrain the allowed region by watching how fast the profile changes after a feeding event, and how far the changes propagate in velocity space. For LB-1, the slow, low-amplitude evolution points to a gentle feeding and a viscosity that spreads material on timescales longer than the orbital period at the line-forming radius. Binarity leaves its own imprint on disks. A companion can truncate the outer disk, confining its radius to a fraction of the orbit's size, or induce warps that tilt parts of the disk out of the plane. If the companion orbits in the same plane, and the separation is moderate, resonances can set a preferred outer radius where the disk ends. Observationally, truncation limits how small the peak separation can become, because the slowest rotating gas that still contributes to the line is then bounded. In LB-1, the observed range of peak separation and the absence of very narrow, sharply peaked emission suggest a disk that does not extend to great radii, consistent with a companion that influences the outer edge. Warps would produce changes in polarization angle and in the relative heights of the peaks, as different parts of the disk move into and out of view. The limited variation in LB-1's polarization and the steady angle argue against strong, rapidly moving warps. Continuum effects from the disk interact with the star's light in ways that photometry already hinted at. A thin, cool disk contributes a small, smooth excess at longer wavelengths, slightly flattening the slope of the spectral energy distribution, from the blue to the near-infrared. It also fills in the deepest photospheric absorption lines, with weak emission from recombining hydrogen, a process called veiling, which makes the lines shallower than they would be from a bare photosphere. Veiling complicates the measurement of projected rotation speed and surface gravity, but careful modelling that includes a disk emission component can recover those parameters. In LB-1, the modest veiling implied by line depths matches the small infrared excess, and together they help bound the disk's density. Interferometry, where available for brighter B stars, directly resolves disks as elongated shapes, aligned with a polarization angle, and spectrostrometry detects tiny shifts in the photocenter across emission lines that betray a rotating structure. While LB-1's brightness places true imaging at the edge of such techniques for many facilities, the spectral signatures alone suffice to infer a thin, rotating equatorial gas layer. The cleanest evidence remains the variable double-peaked emission sitting within broad absorption, the restrained equivalent width, the moderate peak separation, the lack of deep shell features, the small infrared excess, and the stable low polarization. These together delineate a disk that is present cool and thin with internal asymmetries that evolve slowly and with an outer radius shaped by the presence of a companion. The disk is not a mere decoration but a dynamic reservoir whose structure reflects both the star's rapid rotation and the gravitational clock of the orbit. It modulates selected lines without dominating the continuum, it signals the inclination without forcing edge on interpretations, and it provides a context for the radial velocity work to come. With the disk signatures understood, observers can separate the moving fingerprints of the photosphere from the more stationary glow of the gas and then measure how the star's absorption lines swing with time to reveal the tug of an unseen partner. Periodic shifts in photospheric absorption lines provide the first clear hints that a companion tugs on the hot star in LB-1. Each observing run collects spectra at slightly different orbital phases, and after careful calibration, the positions of dozens of hydrogen and helium lines are compared against a template to measure a line of sight velocity for that night. The method rests on cross-correlation, which slides a template spectrum past the data and records how well they match as a function of shift. The peak of the correlation curve marks the velocity that best aligns the features. Because the star rotates rapidly, the individual lines are broad and shallow. So many lines are combined to boost precision. Telluric bands from Earth's atmosphere are masked narrow interstellar lines, provide fixed anchors, and lamp exposures taken before and after the target tie the wavelength scale to a stable reference. Barocentric corrections remove the motion of Earth around the Sun, translating each measurement to a frame centered on the solar system's center of mass. When the velocities from many nights are plotted against time, the points trace a smooth oscillation. The curve crosses a central value and swings to positive and negative extremes, with a near sinusoidal shape, the hallmark of a star, in a nearly circular orbit around a common center of mass. The full range from one extreme to the other gives twice the velocity semi-amplitude, and the time between repeating features gives the orbital period. For LB-1, the period falls in the range of many tens of days rather than a few days, and the semi-amplitude is measured in tens of kilometers per second rather than hundreds, a combination that argues for a companion of moderate influence at a separation large enough to avoid strong tidal distortions of the visible star. To ensure that instrumental drifts and template mismatches are not masquerading as motion comparison stars with similar spectra are reduced with the same pipeline, their velocities remain steady within a few kilometers per second, while the LB-1 velocities shift coherently. Nightly zero points derived from skylines and lamp spectra are subtracted, and repeated observations within a single night show internal consistency. The residual scatter about a best-fitting sinusoid is small compared to the amplitude, an important check that the signal is astrophysical. Line profile diagnostics reinforce the conclusion. In rapidly rotating stars, surface features or pulsations can skew the shapes of lines and produce changes in the bisector, which is the locus of midpoints across a line profile. If the shifts were due to changing line shapes rather than actual motion, the bisector span would correlate with the measured velocity. In LB-1, the bisector spans remain steady, while the centroids of the lines march back and forth, which is consistent with bulk motion of the photosphere rather than profile distortions. The emission from the thin disk behaves differently. Its double-peaked shape varies in relative peak height and subtle asymmetry, but the centroid of the emission does not follow the same sinusoidal path as the absorption. This decoupling indicates that the disk's kinematics are set by rotation around the star rather than by the orbit of the star around the pair, and it allows the absorption velocities to be treated as clean traces of the visible star's motion. Once a robust period and semi-amplitude are in hand, observers fit a Keplerian model to the velocities. For modest eccentricities, the fit returns the period, the time of a chosen orbital phase, the velocity semi-amplitude, and a systemic velocity, which is the velocity of the pair's center of mass relative to the solar system. The systemic velocity provides context for the star's galactic motion, but does not by itself reveal the nature of the companion. The key quantity is the mass function, a combination of the period, the semi-amplitude, and fundamental constants that links the masses of the two bodies and the inclination of the orbit. It can be evaluated from the velocities of the visible star alone, and sets a firm lower bound on the unseen companion's mass for any assumed mass of the visible star. In practical terms, the mass function is small when the semi-amplitude is small, or the period is short and it grows with larger amplitudes and longer periods. For LB-1, the measured numbers yield a mass function that does not force a very massive companion, but the exact inference depends on the mass attributed to the visible star and on the inclination, which is unknown from radial velocities alone. Because the visible star is rapidly rotating and hosts a disk, its mass estimate from spectral type carries uncertainty, and the inclination could be anywhere from low to high, unless other data constrain it. This is where the careful separation of disk and photosphere proves essential. By restricting the velocity measurement to line wings that form deep in the photosphere, and by avoiding epochs where veiling is strongest, the derived semi-amplitude becomes more stable. Observers test the robustness by constructing velocities from independent subsets of lines, such as helium alone or hydrogen alone, and by recomputing the fits after excluding nights with the largest residuals. The period and amplitude persist. Window function analysis checks whether the sampling cadence could have created an alias period, a false peak in power caused by regular gaps in the data. The strongest power remains at the period that phases the velocities into a single coherent curve. The absence of significant photometric modulation at the same period supports an orbit that is not highly inclined and not extremely close, because grazing eclipses and strong ellipsoidal variations would otherwise leave a visible trace in the light curve. With the velocity curve secure, the range of companion types compatible with the mass function can be sketched. If the visible star has a mass typical of an early type star on or near the main sequence, then for moderate inclinations, the companion mass can fall in the range of a compact helium star, or a lower mass hot star whose spectrum is veiled by rotation and faintness. If the inclination is very low, a heavier companion would be required, but very low inclinations are statistically rare unless pointed to by other evidence. The broadness of the visible star's lines makes direct detection of a faint companion's narrow lines difficult yet not impossible. Spectral disentangling methods attempt to separate composite spectra, taken at different phases, into constituent components, by treating the combined light as a sum of two moving templates. Even if the second component is weak, a consistent phase, locked pattern, can build up across many epochs. Before such disentangling, the radial velocity evidence alone remains agnostic about the companion's light. It proves motion and quantifies the orbit of the visible star. It yields a mass function, and it motivates deeper searches that might catch the companion's own lines. The dynamics of the disk offer an auxiliary clue. If the disk is truncated at an outer radius consistent with resonances in a binary that supports the presence of a companion at a separation implied by the orbital period, the peak separation of the red hydrogen emission translates to a characteristic rotation speed in the disk, and when compared to the orbital velocity of the visible star, it can suggest whether the disk extends near the Roche lobe boundary, where tidal forces from the companion limit its spread. In LB-1, the moderate peak separation and the near sinusoidal radial velocities together fit a picture in which the disk is present but constrained, which aligns with a companion at a modest distance. Systematic effects receive close attention. Template mismatch can bias velocities if the template's line depths or widths differ from the target's. Rotational broadening of the template to match the target reduces this bias. Instrument flexure can tilt the wavelength solution. Simultaneous calibration fibers or night sky lines correct for this. Atmospheric dispersion can shift the effective position of the slit with wavelength. An atmospheric dispersion corrector or observations near the meridian minimize the issue. After such safeguards, the remaining uncertainties reflect photon counting noise and small changes in the disk that slightly veil the lines. The core result stands the star's absorption lines swing with a stable period and amplitude, demonstrating that it orbits a companion that contributes little to the observed optical light. Radial velocities therefore supply the first quantitative bridge from spectra to masses. They do not yet identify the companion's nature, but they narrow the possibilities to objects whose masses and faintness in blue light are compatible with the measured curve. They also define the clock that will guide phase-targeted observations in other bands and at higher spectral resolution, so that any faint signature that moves in antiphase to the hot star can be found with the greatest leverage. In a system like LB-1, where the photosphere rotates fast and a thin disk glows quietly, radial velocity work has to be careful and persistent, but when it is, the hidden companion leaves a periodic fingerprint that can be traced night by night until an orbit becomes clear. The earliest full interpretation of the radial velocity curve treats the hot star in LB-1 as a single, visible component whose motion is driven by an unseen partner that adds little or no light in the optical. From the measured period of many tens of days and a semi-amplitude of several tens of kilometers per second, a mass function follows that relates the masses of the two bodies and the unknown inclination of the orbit. To proceed from this lower bound to an actual companion mass, one must assume a mass for the visible star and must adopt or infer an inclination. The visible star's spectrum with strong hydrogen lines, neutral helium and rapid rotation led to a classification as an early type B star with a mass of several times that of the Sun. Its blue-white colour and moderate extinction set a distance that, when combined with the typical luminosity for such a star, supported that mass scale. With those inputs and with an inclination assumed not to be extremely low, the algebra favoured a companion whose mass exceeded ordinary stars by a wide margin. Because no clear spectral lines from a second luminous star appeared in the composite spectra, the companion was proposed to be dark. The simplest dark candidate is a black hole that does not accrete enough gas to shine a non-accreting black hole. The idea gathered force because a very massive black hole in a wide orbit would move the visible star with exactly the slow, near sinusoidal modulation that the data showed while leaving the optical spectrum dominated by the hot star and its thin disk. Archival searches for X-ray and radio emission returned only quiet backgrounds which fit the non-accreting picture if the black hole had no steady source of gas to feed upon. In such a case, the stellar wind from the hot star might cross the companion's path, but the capture of that wind by a distant object can be inefficient, and the resulting accretion rate can be too small to make bright high-energy light. The proposed mass for the dark object expressed as many tens of solar masses carried implications beyond the single system. Massive stellar black holes form when very massive stars collapse, and in the Milky Way's metal-rich environment such stars usually shed large amounts of mass through line-driven winds before they die. A black hole of around 70 times the mass of the Sun would therefore strain common expectations for mass loss in our galaxy. That tension made the claim extraordinary and sharpened interest in its underlying assumptions. Those assumptions were clear and testable. The first was the mass of the visible star. Rapid rotation broadens lines and can mimic some effects of lower gravity, while gravity darkening alters the observed colour. If the star were less massive than assumed, the companion mass inferred from the mass function would fall. The second assumption concerned the inclination. Radial velocities alone cannot fix inclination, but the projected rotation speed of the visible star when compared to plausible equatorial speeds for hot stars can suggest whether the spin axis tilts far from the line of sight. If the inclination were very low, the same velocity amplitude would require a heavier companion. If the inclination were moderate or high, the companion mass would be more modest. The early work explored these ranges and found that for reasonable values the companion mass could remain very large. A further consideration was the absence of a luminous secondary spectrum. In a double-lined pair, narrow lines from a less broadened companion can sometimes be teased from the data, especially in the blue where hot stars shine strongly. Cross-correlation against templates of slightly cooler or more helium-rich stars did not yield a convincing second peak in the earliest pass through the data. That non-detection supported the black hole idea by default, though it left open the possibility of a hot but faint component whose lines were washed out by low signal or by rotational broadening. Distance entered through astrometry and photometric fits. Space-based parallax measurements at the time carried uncertainties at distances of several thousand light-years, and the pipeline solutions for crowded fields sometimes shifted with later data releases. Photometric distances depended on extinction corrections and on bolometric corrections for hot stars that radiate much of their power in ultraviolet wavelengths. Small changes in any of these inputs could nudge the inferred stellar radius and mass. Still within quoted errors, the numbers used in the first full model held together. The disk around the hot star raised a subtle but important question. Could a disk feed a black hole enough to make detectable high-energy light, or would the geometry starve the companion of gas? In a wide orbit, the disk may remain truncated well inside the orbit, and the companion would pass through a region of low-density gas where the accretion cross-section is small. Under that geometry, a non-accreting black hole would indeed be silent. If, on the other hand, episodic outflows seeded denser clumps into the orbit, transient flares might occur. Early high-energy monitoring did not reveal clear flares which did not contradict the Quataert scenario. The observational program that followed the initial interpretation outlined clear tests. Improve the radial velocity sampling to solidify the period and amplitude. Seek weak spectral features that move in antiphase with the hot star. Model the emission line profiles to constrain the disk's outer radius and test for signs of tidal truncation that would fix the orbital scale. Refine the distance and extinction to lock down the visible star's luminosity, radius, and mass. Use polarization and, where possible, interferometry to gauge the inclination of the disk and, by assumption, the orbit. Each of these steps would either strengthen the case for a massive dark companion or push the solution toward lighter, luminous partners. At the moment of proposal, however, the picture was internally consistent. A hot, rapidly rotating star of several solar masses, a stable period of many tens of days, a velocity amplitude of several tens of kilometers per second, a thin disk whose emission behaved like a modest rotating ring, a lack of clear secondary lines, and a quiet high-energy sky, together made a plausible stage for a heavy non-accreting black hole. The claim did not rest on a single oddity, but on a chain of inferences, each modest that multiplied into an extraordinary mass when combined. The appeal of the scenario lay partly in its simplicity. A massive dark companion explained the star's motion, without adding light that the spectra did not show. It fit the silence of the X-ray and radio data. It allowed the disk to remain a property of the visible star rather than a shared structure. It turned the system into a clean dynamical laboratory in which gravity alone revealed the hidden mass. In that frame, the next work to be done was to measure more precisely, to parse more finely, and to revisit every assumption with fresh data, so that the mass function could be translated into a mass with the fewest leaps of faith. Distance enters the chain of inference as soon as brightness and color are measured, because the same star will look faint if it is far and bright if it is near, and dust alters both impressions in steady ways along the path. A parallax from space-based astrometry offers the most direct route, since it measures the tiny shift in position as Earth moves around the Sun and translates that shift into distance with minimal modelling. In practice, the parallax for a star at many thousands of light years is small, and measurement noise crowding by nearby sources and calibration systematics introduce errors that are not negligible. Catalogue releases improve with time as more years of observations are folded in, and as the instrument model is refined, but for a target like LB-1, the fractional uncertainty can still be large enough that the distance range spans a meaningful factor. Even when the parallax seems straightforward, a bias correction is applied because faint stars and crowded fields tend to pull the measured value in systematic directions. Astrometry, therefore, provides an anchor with error bars that must be carried through every later step. Photometry and spectral classification supply independent distance estimates that can test and refine the astrometric result. A spectral type yields an intrinsic color and an absolute magnitude expected for a star with a given temperature and gravity, if seen without dust at a standard distance. The observed color gives the reddening, and an extinction law converts reddening to dimming in the visual band. Subtracting that dimming from the observed magnitude produces a corrected brightness that, when compared to the absolute magnitude, gives a distance. This route is sensitive to the accuracy of the spectral type and to the extinction law along the sightline. For LB-1, the dust column is moderate and standard laws for diffuse interstellar medium often fit, but small variations in grain size distribution tilt the correction by small amounts that matter when distances are propagated into masses. Rapid rotation complicates spectral typing because gravity darkening cools the equator and warms the poles, If the star is seen at a moderate angle, the integrated light comes from zones of different temperature, and the spectrum is a weighted blend that can bias classification toward a cooler or hotter type than the true equatorial or polar value. Line broadening from rotation also reduces the depth of temperature-sensitive features and makes surface gravity harder to fix. Disk emission veils absorption lines and adds a small continuum excess in the red and near-infrared. These factors make the intrinsic color and absolute magnitude less certain than for a non-rotating disk-free star. Observers counter by using multiple classification indicators, by modeling rotational broadening, and by checking for internal consistency across different filters and epochs. Even then, a plausible range remains for the effective temperature and luminosity class, and each combination maps to a different absolute magnitude and therefore to a different photometric distance. Bolometric corrections bridge the gap between visual band measurements and the total energy output of the star. Hot stars radiate much of their light in ultraviolet wavelengths that are not recorded by common ground-based filters, so a correction that depends on temperature and gravity must be added to infer the full luminosity. The correction itself relies on stellar atmosphere models that include line blanketing rotation, and in the case of B stars, a small continuum contribution from a thin disk. If the temperature is uncertain by even a small fraction, the bolometric correction shifts accordingly, and the derived luminosity follows. That luminosity paired with the distance determines a radius through simple relations from stellar structure models. Radius and temperature then imply a mass when evolutionary tracks are consulted. At each turn, the chain links back to distance and to the input classification. For LB-1, different combinations within the allowed ranges can lead to a visible star mass that spans several solar masses. The companion mass inferred from the mass function scales with both the visible star mass and with the sign of the orbital inclination. If the visible star sits at the high end of its allowed mass and the inclination is low, the unseen companion mass rises. If the visible star is lighter and the inclination is moderate or high, the companion mass falls. Distance is therefore not a peripheral detail, it is a lever that moves the entire solution. The astrometric parallax and the photometric distance do not always agree within tiny errors. In crowded fields, blended neighbors can bias the centroid motion used for parallax. In complex sightlines, patchy dust can make a standard extinction law a poor fit. In rapidly rotating stars, gravity darkening alters the apparent temperature enough to shift the bolometric correction. Cross-checks aim to catch these mismatches. Near-infrared photometry suffers less from dust and helps verify extinction estimates. Interstellar absorption lines of sodium and calcium measure column densities that can be compared to reddening inferred from colors. Polarization traces aligned dust and can reveal whether unusual grains might change the extinction curve. When these diagnostics agree that the sightline behaves like a diffuse medium with standard properties, confidence in the extinction correction rises. Another cross-check comes from the dynamics of the orbit itself. If the inclination can be constrained by independent means such as the degree and angle of polarization from an equatorial disk, or the absence of deep eclipses in long light curves, the mass function can be turned into a companion mass range with less freedom. A thin disk that shows modest polarization consistent with a moderate tilt argues against a very low inclination, which would otherwise inflate the companion mass. The peak separation of the deep red hydrogen emission line hints at the disk rotation speed near the star, and under assumptions about the stellar mass and the disk's geometry, can imply a characteristic radius that should not exceed the tidal truncation set by the orbit. If a solution requires a disk to extend beyond that reasonable limit, the distance and mass estimates can be judged inconsistent and revised. Parallax systematics evolve with catalogue updates. Early releases sometimes publish negative or very small parallaxes for distant sources, which when naively inverted produce nonsense or huge distances. Statistical methods that adopt sensible priors for the distribution of stars in the galaxy stabilize the inversion and produce distance estimates with asymmetric uncertainties that are more realistic than simple reciprocals. For LB-1, adopting a prior that reflects its location in the galactic disk and its brightness reduces the chance of overestimating the distance from a noisy parallax. When those statistical distances agree with photometric distances within quoted ranges, the confidence in the visible star's luminosity and mass improves. The companion mass then inherits a narrower range from the mass function. Disk light adds further nuance. Even a small continuum excess in the visual band makes the star appear brighter than a bare photosphere, which would bias a photometric distance to be smaller than the true value if the excess is not removed. Observers fit the spectral energy distribution across blue visual and near-infrared bands with a composite model that includes a hot photosphere and a thin disk, and they solve for the disk fraction that best reproduces the slope. For LB-1, those fits generally find a small disk contribution in the visual band, which nudges the corrected magnitude fainter and the photometric distance slightly larger. The change is not dramatic, but the mass estimates react to even small shifts. In the end, distance and classification, uncertainties do not render the problem intractable. They define a credible range that must be acknowledged when masses are reported. For LB-1, the combined astrometric, photometric and spectroscopic evidence supports a distance in the outer galactic disk and a hot star mass in a moderate range that is consistent with a rapidly rotating early-type star. When these inputs feed the mass function, with a moderate inclination, the companion mass does not require an extraordinarily heavy dark object. If, however, one leans on the far edge of distance and mass, and on a very low inclination, the companion could be driven to very large values. The solution therefore rests on careful weighting of all evidence with distance at its core. As monitoring continues and catalogues refine parallaxes, the allowed space of distances narrows. As disk modelling improves and spectral disentangling isolates more of the photospheric light, the classification tightens. Each gain in precision shrinks the mass range for both components, showing how a quiet point of light in Gemini contains a web of linked inferences, where a small shift in distance can ripple outward until it alters the identity of the unseen companion. Spectral disentangling addresses the problem of two sets of stellar lines, drifting through one another as the orbit proceeds, and it does so by using a time series of spectra taken across many phases to recover two stationary templates whose Doppler shifts and summed light reproduce every observation. The method assumes that each star's intrinsic spectrum remains stable during the campaign, while only the line of sight velocity varies with time. In practice, observers first align all epochs to a common wavelength scale mask. Telluric bands and interstellar lines that do not move with the stars and normalize the continuum, so that broad shape differences do not overwhelm narrow features. Then, either in direct wavelength space or in Fourier space, they solve a set of linear equations that for a trial pair of velocity curves and a flux ratio yields two templates, whose shifted combination fits the data with minimal residuals. Regularization prevents noise from imprinting false structure and bootstrap resampling estimates, uncertainties by repeating the solution on many subsets of the spectra. In LB-1, disentangling begins with the velocity curve of the broad-lined hot star fixed by the radial velocity analysis, while the companion's curve is allowed to vary in amplitude and phase. The procedure searches for a second pattern that moves in antiphase to the broad component and that reduces the residuals around specific wavelength windows where a faint spectrum could hide. The blue region, rich in helium and hydrogen lines, is especially sensitive because even a weak, narrow-lined spectrum can imprint small, phase-locked distortions that the algorithm can gather coherently across dozens of epochs. The first encouraging sign is a reduction in residuals near neutral helium features when a second, much narrower template is allowed. The recovered narrow template shows lines that are too sharp to belong to the rapidly rotating primary and too hot to be a cool dwarf. The lines rise where neutral helium is expected and weaken where metals often dominate in cooler stars. At the same time, the template lacks strong signatures of singly ionized helium that would mark an extremely hot photosphere. This balance points toward a stripped helium star whose surface layers have been peeled by prior mass transfer, leaving a hot compact object with relatively sharp lines because its rotation is modest. As the solution stabilizes, the second component's velocities settle into clear antiphase motion with the broad-lined star and the amplitude given a mass ratio through the simple relation that the product of mass and velocity amplitude is the same for both bodies in a circular orbit. The derived mass ratio does not demand an extraordinarily heavy dark object. Instead, it favors a secondary with stellar mass in the range expected for a helium star produced by envelope stripping. The flux ratio across the blue window is small, consistent with the narrow template contributing only a minor fraction of the total optical light. That small fraction explains why the second set of lines escape direct visual detection in single epochs, and why cross-correlation against generic templates failed to pull out a stable peak at earlier stages. The narrow template also shows subtle nitrogen enhancement and carbon depletion relative to solar composition, a pattern often seen in material that has undergone hydrogen burning by the carbon-nitrogen-oxygen cycle and then reached the surface through mass loss. Such abundance hints strengthen the stripped interpretation without requiring detailed atmospheric modelling beyond the scope of the extraction. Importantly, the emission from the thin disk anchored by the deep red hydrogen line does not align with the narrow template and does not track its motion. Instead, the disk emission remains tied to the broad-lined star as expected if the disk forms from gas shed by the rapidly rotating primary. This separation of responsibilities, the broad absorption and the disk belonging to the primary, the narrow absorption belonging to the secondary, simplifies the geometry and supports the assumption that each template is stable over the observing span. Tests that alter the set of masked pixels shift continuum placements, or exclude epochs with the strongest disk variability produce nearly the same narrow template and the same antiphase velocities, which argues that the result is not an artifact of veiling or normalization. Alternative hypotheses, such as a single star plus a dark massive companion with no light, fail to reduce the phase-locked residuals in the helium windows once the broad template is fixed. The data simply prefer a faint moving spectrum. With two velocity curves in hand, the mass function splits into individual masses after an inclination is adopted. Independent indicators suggest a moderate tilt. The polarization magnitude is small, but non-zero shell profiles are absent, and no deep eclipses appear in the long baseline photometry. Under such inclinations, the measured mass ratio and period yield a primary of several solar masses and a secondary of lower mass consistent with a compact helium star. The systemic velocities derived independently for both templates agree within uncertainties, and the phase zero points align with the photometric ephemeris, small consistency checks that would be difficult to satisfy if the second component were a spurious mixture of disk features or telluric residuals. Disentangling also clarifies the projected rotation speeds. The broad template requires rotational broadening of several hundred kilometers per second to match the wings of hydrogen and helium lines, while the narrow template fits best with modest broadening, implying a secondary that spins relatively slowly. Slow rotation in a stripped helium star is natural if angular momentum was shed with the envelope during mass transfer, or if the star has since spun down through winds. The temperature difference between the templates explains the earlier difficulty reconciling a single photospheric type with the exact depths of select helium lines. The composite light blended two different atmospheres in proportions that varied with wavelength. Once separated, each template's line ratios fall into coherent sequences that can be compared with atmosphere grids to refine temperatures and gravities. Those refinements then feed back into the flux ratio as a function of wavelength, improving the distance-independent constraints on luminosities. The robustness of the solution rests on coverage. Spectra sample the orbit across many cycles, ensuring that no single season dominates and that aliases are suppressed. Signal to noise is high enough in the blue to let weak lines add coherently. The spectral resolution resolves narrow features to a few resolution elements, preventing them from being washed entirely into the broad profiles. Residual checks show no phase-locked pattern left behind after shifting and summing the two templates except within the cores of the deep red emission, which were masked from the start since the line is circumstellar rather than photospheric. When the narrow template is shifted to the primary's velocity and subtracted from the data, the fit worsens. When it's shifted to antiphase and included, the fit improves. Such reversals tried across multiple windows confirm that the secondary's motion is real and in antiphase. Uncertainties remain as they must. The flux ratio has error bars that grow toward the red, where the disk adds continuum. The abundance pattern is only sketched, not measured to high precision, because rotational blending in the primary limits the depth of the windows left for the secondary. Telluric residuals near some helium features are minimized but not eliminated, and they widen the uncertainties when clouds or high air mass intrude. Yet within these bounds, the central picture holds the spectra of LB-1 resolve into a broad, rapidly rotating early-type star that carries a thin decretion disk and a faint, narrow-lined hot companion that moves in antiphase with velocities consistent with a stripped helium star. This picture removes the need for a massive silent black hole to explain the radial velocity curve. Gravity still rules the orbit, but the partner is now luminous, if only slightly, and its presence can be traced directly in the light, rather than inferred solely from the motion of the primary. With two stellar templates recovered, subsequent analyses can refine temperatures, gravities, and the mass ratio, and they can revisit earlier photometric and polarimetric constraints with the new knowledge of the flux ratio in hand. For the purposes of the current step, however, the essential outcome of disentangling is secure. Two stars speak in the spectrum, one loud and broad, one quiet and narrow, and their antiphased voices together reproduce the time series with fewer assumptions and smaller residuals than any model with an invisible, extremely massive companion. The emerging picture of LB-1 settles into a coherent physical system, in which a rapidly rotating early-type star dominates the optical light, while a fainter, hotter, stripped helium star orbits in antiphase, and a thin equatorial disk surrounds the broad-lined primary. The spectra passed at rest show hydrogen, with wide wings and neutral helium at expected strengths for a hot photosphere, and the projected rotation speed inferred from the flattened cores points to equatorial velocities of several hundred kilometers per second, when inclination is considered a hallmark of stars that can support a decretion disk. The deep red hydrogen line displays double-peaked emission, whose separation and variability imply a rotating, nearly Keplerian gas layer of modest radial extent, consistent with truncation by a companion at a separation set by an orbital period of many tens of days. The narrow-lined component extracted by disentangling carries helium features that are too sharp to belong to the primary, and shows hints of nitrogen enhancement with carbon depletion, a pattern that often marks material processed by the carbon-nitrogen-oxygen cycle, now visible at the surface because a prior phase of mass transfer peeled away the hydrogen-rich envelope. This luminous but faint secondary contributes only a small fraction of the optical flux, especially in the blue where the primary shines strongly, which explains the earlier absence of a clear second set of lines in individual spectra. With two velocity curves recovered, the mass ratio follows from the inverse ratio of the velocity semi-amplitudes, and for moderate inclinations the numbers favour a primary with a mass of several times the mass of the Sun, and a secondary of lower mass consistent with a compact helium star, rather than an extraordinarily massive dark object. The systemic velocity from both templates agree within uncertainties, and their phases align with the radial velocity ephemeris built from the primary's lines, small but telling checks that the two components share the same orbit around a common centre of mass. Photometry remains steady to within small margins over months and years, with no deep repeating dimmings that would indicate eclipses, which in turn suggests an inclination that is neither edge-on nor very low. Polarization sits at a modest level with a stable angle, the behavior expected for electron scattering in a flattened disk seen at intermediate tilt. The absence of shell profiles in the deep red hydrogen line supports this geometry. The line of sight does not graze the disk mid-plane, so a deep, narrow central absorption is not present. Near-infrared colours show at most a slight excess over a pure photosphere, indicating that continuum emission from the disk is weak, which dovetails with the restrained equivalent widths of the hydrogen emission lines, and with the small veiling of the primary's absorption. Together these clues portray a disk that is cool and thin, slowly evolving in internal asymmetry, but not flaring dramatically, and limited in outer radius by tidal forces from the companion. The dynamics of the pair fit comfortably within standard binary evolution pathways. A system that began with two hot stars of unequal mass can pass through a stage where the initially more massive star fills its Roche lobe as it evolves and transfers mass to the companion. That transfer spins up the recipient to near critical rotation, enabling a decretion disk while stripping the donor of most of its hydrogen envelope and exposing a helium-rich core that becomes a compact helium star with relatively sharp spectral lines. The present-day LB-1 spectrum mirrors this outcome. The fast rotator with the disk is now the more luminous star in the optical, while the stripped star, though hot, contributes a smaller share of light in the blue and visual bands. The orbital period of many tens of days implies a separation large enough that tides no longer force strong ellipsoidal distortions, which explains the lack of pronounced photometric modulation. The nearly sinusoidal radial velocities with small residuals point to a low eccentricity orbit, consistent with past mass transfer that circularizes the motion. The mass function computed from the primary's velocities alone never required a heavy companion if the primary mass and inclination lived within moderate ranges. The detection of the secondary's own lines now removes the remaining freedom by fixing the mass ratio and lowering the allowed companion mass into a regime natural for a stripped star. High-energy observations add a quiet backdrop. X-ray and radio searches do not reveal persistent sources at the position of LB-1 in line with the absence of a bright accretion flow. In the revised picture, there is no massive silent black hole to accrete from the wind or the disk. The secondary is luminous in its own right but faint. Even if a compact remnant were present, the inferred masses and the lack of high-energy signatures argue against a heavy non-accreting object that would have been demanded by the earliest assumptions. The disk's behavior reinforces this view. The range of peak separations in the deep red emission and the lack of very narrow, sharply peaked profiles indicate that the outer disk does not extend to radii that would be difficult to maintain in a wide, unconstrained environment. Instead, the likely tidal truncation by the companion keeps the disk within a radius compatible with the measured period and velocities. That truncation changes slowly as seen in the gentle breathing of the line-forming region, inferred from small shifts in peak separation without evidence for violent interactions that might hint at a deep potential well of an extremely massive dark neighbour. Modelling of the composite spectral energy distribution with a hot stellar atmosphere for the primary, a helium star atmosphere for the secondary, and a small disk continuum confirms that only a minor adjustment to the visual flux is needed to account for the infrared slope, and this adjustment nudges photometric distances and luminosities slightly, without overturning the moderate mass scale for either component. The revised system picture, therefore, is not a dramatic abandonment of prior data, but a reweighting of evidence as new techniques pull faint signals from beneath broad features. The hottest lines that once seemed to require a single, very massive partner now share the stage with a second, sharper voice, whose antiphase motion and chemical hints tell a clear evolutionary story. The early path that led to a massive dark interpretation relied on adopting a higher mass for the visible star and allowing for inclinations that drove the unseen companion upward in mass. The present path replaces those allowances with direct detection of the companion's light and motion, thereby shrinking the uncertainty space until the heavy dark solution is no longer favoured. Within this clarified framework, each observable finds a place. The broad hydrogen wings and neutral helium ratios set the primary's temperature and gravity after accounting for veiling. The projected rotation speed and gravity darkening explain the line shapes and the feasibility of a disk. The double-peaked emission constrains disk kinematics and orientation. The antiphase narrow helium lines trace the secondary fix the mass ratio and hint at processed material on its surface. The near sinusoidal radial velocities establish the period, confirm a low eccentricity, and yield the systemic velocity. The low amplitude, steady photometry, and small polarization pin the inclination within a moderate range. The absence of high-energy emission and of deep eclipses fits the geometry and the nature of the companion. All of these pieces interlock to remove the necessity for an extraordinary, massive, non-accreting black hole. The system stands as a binary of a rapidly rotating B-type star with a thin disk and a compact stripped helium companion on a nearly circular orbit of many tens of days. This arrangement is both physically plausible and observationally supported, and it provides a calm, consistent base for the next steps that refine temperatures, gravity's radii and masses within the tightened bounds set by direct spectral separation. Orbital dynamics enters once the period velocity amplitudes and systemic velocity are securely measured, because these quantities tie the visible motions to the gravitational pull that binds the pair in LB-1. The phase-folded radial velocities of the broad-lined primary describe a near sinusoid, with a period of many tens of days, and the small residuals around a circular model suggest that any eccentricity is mild. A circular or nearly circular orbit is expected if a past episode of mass transfer has acted for long enough to dissipate orbital energy and angular momentum in shocks and tides, leaving the pair to revolve in a smooth, regular path. The velocity semi-amplitude of the primary measured in tens of kilometers per second fixes the size of the primary's orbit around the common centre of mass, when combined with the period through simple kinematic relations. A longer period at a given amplitude implies a larger orbit, while a shorter period implies a tighter one. The systemic velocity, which is the velocity of the centre of mass relative to the Sun, tells how the pair drifts through the galaxy, but does not affect the internal dynamics. With the secondary now detected as a narrow-lined helium star moving in antiphase, its own semi-amplitude supplies the mass ratio directly, because in a two-body system the product of mass and velocity amplitude matches for both stars when the orbit is circular. The ratio of amplitudes therefore gives the inverse ratio of masses, and together with the period it yields the linear dimensions of both orbits projected along the line of sight. Geometry then enters through inclination, the tilt of the orbital plane relative to the observer. Inclination multiplies the true velocities by the sine of the tilt, so angles well away from edge-on reduce the projected amplitudes without changing the true gravitational balance. Independent indicators such as modest polarization from an equatorial disk and the absence of eclipses point to a moderate inclination, neither very small nor near 90 degrees, which keeps the derived masses within a reasonable range. From these pieces a mass function can be evaluated in both directions, one from the primary's velocities and one from the secondaries, each providing a consistency check. The two evaluations agree within uncertainties when the flux ratio and line veiling are accounted for, reinforcing that the disentangled curves are tracing the same clock. The semi-major axis of the relative orbit follows from Kepler's third law once the total mass is set by the mass ratio and an inclination is adopted. That semi-major axis, expressed in units of the Sun-Earth distance for intuition, but always converted to consistent physical units in calculation, translates into a scale against which the disk size can be judged. The deep red hydrogen emission, whose double peak separation reflects the rotation speed at the line-forming radius, suggests that the disk extends to a modest fraction of the orbital separation as expected if tidal resonances from the companion truncate the outer edge. The absence of very narrow peaks argues against a disk that approaches the Roche lobe, the gravitational boundary, within which material remains bound to the primary. The measured peak separations change slowly with time, indicating that the effective radius where most of the red hydrogen photons arise breathes gently as the disk density drifts, but the outer edge remains within a range compatible with a stable truncation. The small or absent eccentricity has practical consequences for line profiles across the orbit. In an eccentric orbit, the radial velocities would depart from a sinusoid, and the time spent near periastron would be shorter than the time near apastron, imprinting a subtle skew in phase plots. The observed symmetry in phase and the near sinusoidal shape point to a near circular path. The argument of periastron becomes undefined in strict circularity, simplifying the parameter set. The time of conjunction, when the primary lies between the secondary and the observer or vice versa, can be identified from the phases where the radial velocities cross the systemic value, and the relative phasing of subtle line shape changes sometimes indicates which star approaches or recedes at each conjunction. In LB-1, the disk emission tied to the primary remains largely insensitive to the conjunction phase, another sign that the orbit is wide enough to avoid strong tidal distortions on orbital timescales. With masses and semi-major axis in hand, one can compute expected rotational velocities for Keplerian motion at various radii in the disk and compare them to the observed peak separations. The comparison supports a disk that rotates nearly as a set of test particles in the primary's gravity, with small deviations that could reflect viscosity or spiral density waves. The dynamical timescale at the line-forming radius set by the Keplerian period there is much shorter than the binary period, which explains why the disk can reorganize its internal asymmetry without immediate reference to the orbital phase. The thermal timescale, which controls how quickly the disk radiatively relaxes after a density change, is longer than the dynamical time, but still shorter than a year for thin ionized gas at these radii, fitting the measured pace of v/r variability. The angular momentum budget implied by the mass ratio provides a further check on plausibility. A primary spun up by past mass transfer should carry a significant fraction of its critical rotation, where the equatorial gravity and centrifugal force nearly balance. The projected rotation speed measured from the broad lines combined with an inclination in the moderate range yields an equatorial speed that approaches a few tenths of the critical value, enough to support steady feeding of a decretion disk without immediate ejection. The secondary's modest projected rotation speed is natural if much of its angular momentum left with the stripped envelope, or if subsequent winds have spun it down. This contrast in rotation is not only consistent with the evolutionary story, it also stabilizes the disentangling solution by keeping the secondary's lines narrow and distinguishable from the primary's broad profiles. Orbital stability over many cycles argues that mass loss through winds or the disk is not large enough to shift the period measurably on the timescale of the campaign. Period searches that allow for a linear drift find no significant change beyond the measurement errors constraining any mass leakage from the system to be low. The systemic velocity measured independently from both templates matches within uncertainties and shows no trend, which again points to a steady configuration. Tidal forcing in a near-circular moderate separation orbit is weak, so the absence of tidally driven pulsations in the line asymmetries is unsurprising. The rotational flattening of the primary and gravity darkening remain, as the dominant photospheric effects and their influence is static across the orbit on the timescales considered. Orbital dynamics also sets expectations for any small reflex motion that might be seen in precise astrometry. The semi-major axis of the primary's orbit projected on the sky, measured in microarc seconds for a distant system, could in principle be within reach of future space-based missions, but present astrometric catalogues at this distance and magnitude do not resolve it, leaving spectroscopy as the primary dynamical tool. Finally, the dynamical configuration integrates cleanly with the absence of high-energy emission. In a wide near-circular orbit with a stripped helium companion that does not fill its Roche lobe, there is no obvious engine for bright accretion onto a compact object, and none is required by the masses now inferred. The orbital solution therefore performs a central role. It sets the scale of the system, fixes the mass ratio, constrains the inclination through independent observables, and provides a clock by which all time-dependent phenomena can be phased and tested. In this calm arrangement, gravity describes a two-star dance, in which a fast disk hosting primary and a faint hot helium secondary revolve with steady cadence, their paths and speeds measured from the periodic shifts of their lines, and their separation set by a period long enough to keep tides quiet and disks thin. Binary evolution provides a framework that links the present-day properties of LB-1 to earlier phases when mass and angular momentum were exchanged, and in this framework a simple, physically grounded path can account for a rapidly rotating hot primary, with a thin disk and a faint hot narrow-lined secondary that shows signs of processed material. The path begins with two hot stars born in the galactic disk, with an initial mass ratio not far from unity, and an orbital separation that allows one star to expand enough to touch its gravitational boundary, called the Roche lobe as it evolves off the main sequence. The initially more massive star climbs toward cooler temperatures and larger radii, and when its radius matches, the Roche lobe gas flows through the inner Lagrange point onto the companion. This mass transfer can be stable if the donor star responds to mass loss, by shrinking back within its lobe, or unstable if expansion continues and a brief common envelope phase ensues. In the stable channel, the transfer proceeds on a thermal or nuclear timescale, spinning up the accretor as angular momentum comes with the gas. The accreting star brightens and moves blueward in the color magnitude diagram, and its equatorial speed can approach a large fraction of the critical value where centrifugal force counterbalances gravity at the equator. Near critical rotation promotes the formation of a decretion disk. Small episodes of mass ejection from the equator place gas into orbit, and a viscous process spreads that gas into a thin, nearly Keplerian disk. The donor star, meanwhile, is stripped of most of its hydrogen envelope, leaving a compact helium-rich core with a hot photosphere and relatively sharp lines if its rotation has been modestly braked. The orbital period adjusts as mass is rearranged between the stars. If mass flows from the initially heavier star to the lighter companion, conservation of angular momentum can shrink the orbit, but mass loss from the system through winds or through outflows can widen it. The balance of these effects depends on mass loss rates, the specific angular momentum carried by the escaping gas, and the efficiency with which matter crossing the inner Lagrange point is actually accreted. In systems that mature into a B+ stripped helium configuration, the orbits commonly settle into periods of many tens of days to a few hundreds of days, wide enough to avoid strong tidal distortions, and yet close enough that resonances can truncate the disk around the fast rotator. LB-1's measured period of many tens of days and its low eccentricity are typical of this outcome, and are consistent with a past transfer phase that circularized the orbit. Chemical fingerprints provide a second line of evidence for stripping. When a star burns hydrogen through the carbon-nitrogen-oxygen cycle, nitrogen is enhanced and carbon and oxygen are depleted in the layers near the core. If mass loss removes the outer hydrogen layers, the processed material can reach the surface and imprint the spectrum. The narrow-lined secondary in LB-1 shows hints of nitrogen enhancement and carbon depletion relative to solar composition, which aligns with a helium star whose envelope has been peeled. The temperature of such a star is high, and its radius is smaller than that of a main sequence star of similar temperature, which makes its optical flux a small fraction of the total compared to the bright, rapidly rotating primary. These properties explain why the secondary's lines are faint and narrow, why they are most easily seen in the blue, where helium transitions are strong, and why they move in antiphase with an amplitude consistent with a lower mass than the primary. Angular momentum evolution ties the narrative together. The accretor gains spin as it gains mass. If the transfer rate is high and sustained, the accretor can reach near critical rotation and maintain it for a long time, feeding a decretion disk even after transfer subsides. The donor can lose spin because angular momentum leaves with the mass, and winds from a compact helium surface can further slow rotation. This contrast between a fast primary and a modestly rotating secondary matches the disentangled line widths in LB-1. The present-day modest polarization with a stable angle, the absence of deep shell absorption in the deep red hydrogen line, and the small near-infrared excess suggest a disk that is geometrically thin and not viewed edge on which is natural if the disk formed from near-critical rotation rather than from ongoing strong interaction. Population synthesis models which simulate large ensembles of binaries with varied initial masses, separations and mass transfer efficiencies predict that B+ stripped helium pairs are not rare outcomes for hot binaries. They also predict that such systems should show near circular orbits if mass transfer has been stable for long enough that the helium companion often contributes little optical light, and that disk truncation signatures should appear in emission line profiles. LB-1 matches these expectations in outline. The details such as the exact mass ratio and inclination tune where it falls within the predicted distribution, but nothing requires unusual physics beyond standard prescriptions for wind mass loss, angular momentum transport, and radiative envelopes. Timescales in this pathway are instructive. The initial main sequence lifetimes of stars of several solar masses are measured in tens of millions of years. The mass transfer phase lasts for a shorter slice set by the thermal adjustment timescale of the donor, which can be as short as hundreds of thousands to a few millions of years depending on the mass and structure of the envelope. After transfer, the helium star spends a time in the helium burning phase that is shorter than the hydrogen burning stage by a factor of several again, of order a few millions of years. The B phase of the accretor can persist so long as rapid rotation is maintained and small injections of mass supply the disk. It can be intermittent with disk build-up and decline cycles visible as changes in emission line equivalent widths and peak separations. LB-1's restrained variability and steady polarization indicate a settled state rather than a dramatic outburst phase, which is consistent with a mature system well past the most intense transfer. Energetics and geometry govern whether any residual interaction remains. In a near-circular orbit of many tens of days, the Roche lobes are well outside the photospheres, so direct overflow is not expected now. Winds from the helium star could in principle graze the primary's disk or stir its outer parts, but the observed calm in the emission profiles argues for only gentle perturbations. The disk outer radius inferred from emission peak separations and their slow changes lies within a fraction of the orbital separation that is compatible with tidal truncation at a low resonance, which supports a picture in which the companion sculpts the disk edge but does not drive strong shocks. The lack of bright, high-energy emission adds a final constraint. There is no sign of a compact object accreting at a high rate. The evolutionary channel that produced a helium companion, rather than a silent, heavy dark remnant, avoids this expectation naturally. Kinematic and structural consistency checks follow. The mass ratio from antiphase velocities combined with a moderate inclination, inferred from polarization, and the absence of eclipses yields component masses that lie within ranges predicted for a spun-up B-type primary and a stripped helium secondary produced by stable non-explosive transfer. The systemic velocity and location in the galactic disk match a population of relatively young massive binaries that have not wandered far from their birthplaces. The near sinusoidal radial velocities, the small residuals to circular fits, and the absence of tidally driven pulsations in line bisectors indicate a system in dynamical equilibrium. Within this pathway, uncertainties remain limited and explicit. The exact mass transfer efficiency, the specific angular momentum of escaping gas, and the internal mixing in the primary during spin-up all affect the present-day rotation and luminosity. The degree of nitrogen enhancement and carbon depletion in the secondary awaits higher signal measurements in less veiled windows to quantify precisely. The inclination range derived from polarization and photometry could be narrowed by long baseline interferometry of the disk or by precise spectrostrometry across the deep red emission which would further tighten masses. None of these uncertainties, however, upset the overall evolutionary picture. They are refinements that sharpen parameters within a model that already accounts for the principal observables. Thus, the stellar evolution pathway that leads to LB-1's present state is a sequence of well-understood steps too. Hot stars begin in a moderately wide orbit. The initially heavier star expands and transfers mass. The companion spins up to near critical rotation and builds a thin truncated disk. The donor is stripped to a hot helium star that contributes little optical flux. The orbit circularizes and settles into a period of many tens of days. The spectra record one broad rotating photosphere with disk emission and one faint narrow-lined helium star in antiphase. In this settled configuration, the system reads as an evolved binary, shaped by mass transfer rather than as a hot star pulled by an extraordinarily massive non-accreting dark companion. The calm coherence of the present-day data is the natural signature of that path. A silent compact object remains a logical possibility in any binary, where one star's motion is measured cleanly, but the partner is faint. So the question becomes how much room is left in LB-1 for a non-accreting black hole or neutron star once the narrow-lined helium companion is detected and the orbit is fixed. The first constraint arises from the mass ratio and the velocity amplitudes, because the antiphase motion of the narrow component demonstrates that it carries a finite share of the system's light and mass. For a silent black hole to hide in the same orbit without betraying itself in the spectra, a third body would have to participate, or the narrow component would have to be misidentified emission or scattered light rather than a true photosphere. The coherence of the narrow lines across many cycles, their helium-dominated pattern, their modest rotational width, and their matching systemic velocity all argue that they belong to a star. With two luminous bodies already accounted for the dynamical allowances for an additional heavy unseen mass shrink. A triple configuration could, in principle, place a compact object on a wider or tighter orbit, but the near-sinusoidal radial velocities of both visible stars, the small residuals to a two-body fit, and the absence of long-term drifts in the systemic velocity argue against a strong third-body influence over the observing span. High-energy limits supply a second constraint. A compact object embedded in the wind of a hot star can accrete through gravitational focusing even when there is no Roche overflow, and simple estimates of wind density, relative speed and capture, cross-section produce a range of accretion rates. In wide orbits, the rate can be small, yet for a very massive black hole the gravitational focusing increases. The absence of persistent X-ray or radio emission down to standard survey limits does not by itself exclude an accretion rate much lower than these estimates. But when combined with the evidence that the secondary is luminous and hot, the expectation of even weak accretion signatures becomes harder to maintain. A neutron star introduces further subtleties because magnetic fields and spin can quench accretion at low rates, but then intermittent flares or pulsations may appear. None do. The disk around the primary acts as a third diagnostic. Tidal truncation implied by the period limits the outer disk radius to a fraction of the separation. If a heavy compact object shared the orbit, its gravity would enhance truncation and stir spiral waves that leave distinct phase-locked asymmetries in the deep red hydrogen profiles. The observed V over R variability drifts slowly and does not lock to the orbital phase, which fits a one-arm density wave in a thin disk, rather than a strong compact perturber near the line-forming region. The peak separations and their restrained modulation point to rotation speeds and radii compatible with a disk governed mainly by the primary's gravity and by smooth tidal resonances with the detected secondary, not by close passages of an additional massive body. Light curve morphology offers a fourth check. Ellipsoidal variations arise when tides elongate a star, and they produce a double-peaked modulation at half the orbital period. Their absence at measurable levels in long baseline photometry suggests that neither star is forced into a strong tidal distortion, which is natural at the measured separation, but it also argues against a hidden inner companion that would raise the distortion frequency or add shallow eclipses. Polarization behavior adds a fifth thread. Electron scattering in a thin disk viewed at moderate inclination imprints a small stable polarization with an angle aligned to the disk plane. A compact object interacting strongly with the disk would induce warps and rapid angle changes. None are seen beyond modest drifts shared with slow changes in the emission line asymmetry. Astrometric stability contributes a sixth line of evidence. While present catalogues may not resolve the small reflex motions of the components, over a single orbit at this distance they do constrain large accelerations that a very heavy closed third body would impose. The lack of a measured long-term proper motion anomaly, consistent with a massive tight companion, aligns with the two-body solution. Chemical patterns in the narrow line spectrum offer a seventh indirect test. Nitrogen enhancement and carbon depletion at the surface of the secondary indicate processed material now exposed by stripping and evolutionary tracks that yield such surfaces at the measured temperatures, and gravities produce masses that sit comfortably below the many tens of solar masses once proposed for a silent black hole. To force a heavy dark companion back into the model would require pushing the inclination to very low angles and the primary mass to high values, while simultaneously denying the stellar nature of the narrow lines. These moves contradict the polarization. The absence of deep eclipses the modest near-infrared excess and the internal consistency of the disentangling. Residual uncertainties remain, and they define the true scope for a quiet remnant. The flux ratio as a function of wavelength still carries error bars, especially in the red where disk veiling rises. If the secondary were dimmer than current templates, suggest its mass could be slightly higher at a given inclination, which would marginally increase the allowed space for an additional unseen mass at larger separation. Likewise, if the inclination were closer to face-on than polarization, and the lack of eclipses imply all masses would inflate. However, statistical priors disfavor extremely low inclinations, and independent geometric indicators keep the tilt within a moderate band. Another subtlety concerns the possibility that the narrow-lined object is itself a compact helium star on the path to becoming a white dwarf, leaving open the question of whether a later supernova could add a compact remnant to the system in the far future. That prospect concerns future evolution, not the present composition. In the present, the spectra velocities and photometry are most naturally explained by two luminous stars and one thin disk in a near-circular orbit. One can ask what a truly non-accreting black hole would look like here if it were allowed. It would add mass to the gravitational balance without light increasing the velocity amplitudes at a fixed period. But those amplitudes are measured, and when the luminous secondary is included, the remaining headroom for an extra massive contribution is small. It would also interact with winds and with the disk, yet the quietness of the high-energy sky and the ordered emission profiles leave little trace of such interaction. Finally, it would imprint slow accelerations on the systemic velocity or on the relative phasing if it orbited on a longer cycle. The systemic velocity shows no trend across the campaign. Thus, the silent black hole scenario, while conceptually simple, contracts to a narrow corner where inclinations of very low distances sit at the far edge of uncertainties and the narrow spectrum is discounted. The data do not prefer that corner. Instead, they prefer the stripped helium companion that moves in antiphase and carries the chemical and kinematic signs of its history. What remains uncertain is not the presence of a luminous secondary, but the precise temperatures, gravities, and element ratios of both stars, the exact disk, viscosity and feeding rate, and the small eccentricity that future precision might reveal. Those uncertainties matter for detailed modelling of evolution and mass loss, yet they do not restore the need for a heavy, non-accreting black hole. In LB-1, the room for a silent, compact object shrinks to an academic exercise, bounded by geometry, and by the clarity of two voices in the spectrum, while the working picture rests on a pair of stars whose light and motion explain the observations without invoking an extraordinary hidden mass. Claims that a hot star hides a massive non-accreting companion have appeared in other systems, and the paths by which those claims are tested offer a set of techniques that map neatly onto the case of LB-1. A prominent comparison comes from a bright target in the southern sky, where early radial velocity work and composite spectra were first read as a hot star orbited by a dark object of large mass. As in LB-1, the visible component showed broad hydrogen lines and signs of rapid rotation, and emission in the deep red hydrogen line suggested a thin rotating disk. The radial velocities appeared near sinusoidal with a period of many tens of days, and no obvious secondary spectrum leapt from single epoch data. The simplicity of a massive faint partner drew attention because it seemed to explain the motion without adding light. Yet the same observables that once pointed toward darkness later yielded a different resolution, when spectral disentangling high angular resolution and careful modelling of disk signatures were brought to bear. Time series spectroscopy across many orbital cycles allowed the blended fingerprints to be separated into a broad fast component and a faint narrow hot component moving in antiphase, a result mirrored in LB-1. Interferometry, which measures the fringe pattern from widely separated telescopes to resolve sources at scales far smaller than a single mirror can reach, then constrained the geometry by detecting elongation or small photocenter shifts consistent with the two-star system, rather than with a lone luminous star tugged by an unseen mass. Spectrostrometry, a technique that tracks the position of the photocenter as a function of wavelength across emission and absorption lines, provided complementary evidence by revealing tiny phase-dependent offsets that only a luminous companion could produce. Polarimetry added orientation by fixing the angle of a flattened disk on the sky and tying it to an inclination range that made extremely low tilt unlikely. Together, these tools shifted the weight of evidence away from an extraordinary dark companion and toward a more ordinary pair shaped by mass transfer, a narrative that rhymes with the revised picture of LB-1. The lessons from that southern case extend beyond its specific numbers. First, single-lined radial velocities in rapidly rotating hot stars can be misleading when considered alone, because projected rotation smears temperature-sensitive features and disk-veiling shallows cause, both of which can bias spectral typing, and therefore the assumed mass of the visible star. Second, the absence of obvious secondary lines in individual spectra is not evidence of absence when a hot but faint star with narrow lines contributes only a small fraction of the light. Disentangling can recover such a spectrum by stacking weak, phase-locked distortions coherently provided that the time sampling covers the orbit well and that telluric and interstellar lines are masked to avoid false periodicities. Third, the behavior of the deep red hydrogen emission must be decoupled from the orbital clock. V/R cycles in a thin disk can drift on timescales unrelated to the period because one-armed density waves precess slowly. If those cycles are misread as orbital modulation, they can bias velocity fits or be mistaken for evidence of an additional perturber. Fourth, parallax and photometric distances evolve with catalogue updates and improved extinction maps, and their uncertainties propagate directly into mass estimates. Conclusions that rely on edges of distance ranges should be revisited when improved astrometry appears. Fifth, polarization and the presence or absence of shell features provide practical independent limits on inclination that keep mass estimates from wandering into face on extremes that would otherwise inflate unseen companions. Other hot star systems with disks reinforce these points by contrast. In a few binaries where a compact remnant is present, Faint X-ray emission or occasional radio flares accompany specific orbital phases when wind capture rises and the disk profiles show sharper phase-locked asymmetries or transient shell episodes. Where such signatures appear, they add to the gravitational evidence and keep the interpretation self-consistent. Where they do not, the burden shifts to more sensitive searches and to direct detection of a luminous partner. In many B+ helium systems, the helium star emerges with narrow helium-rich lines, and mild nitrogen enhancement precisely the pattern disentangling exposes in LB-1. The distribution of orbital periods in such pairs also clusters at many tens to a few hundreds of days, again matching the cadence found in LB-1 and in the southern comparator. These parallels do not prove identity, but they provide context in which the measured properties of LB-1 look ordinary for a mass transfer product, rather than exceptional for a dark massive object. Methodological checks performed in the southern case, and applicable here, focus on robustness. Velocity curves are rebuilt from independent line lists such as helium only or hydrogen only to test sensitivity to veiling and to disk contamination. Templates are broadened to match projected rotation and are perturbed in temperature and gravity to measure how much the inferred velocities shift under plausible classification errors. Window functions are computed for the time sampling to identify alias periods that can appear when gaps recur at sidereal intervals. Residuals are phased not only to the best period, but also to nearby aliases to confirm that the coherent signal resides at a unique frequency. The same suite of tests applied in LB-1 shores up the period and semi-amplitudes and reduces the risk that cadence rather than gravity writes the curve. High angular resolution work in the southern target also supplied a cautionary tail blended light from a wide unrelated neighbour, can bias both photometry and astrometry if the aperture includes more than one star. Careful point spread function fitting and checks against crowded field catalogues filtered such contamination. In fields as calm as Gemini around LB-1, this risk is smaller but not zero. The repeated confirmation that a single point source dominates the position and that background stars do not intrude on the slit strengthens confidence that the measured spectra belong to the target. Disk modelling provides another bridge between cases. In both systems, the separation of the deep red emission peaks and their slow evolution argue for disks truncated by resonances with a companion at radii that are a modest fraction of the orbital separation. Radiative transfer models of thin isothermal disks in quasi-Keplerian rotation reproduce the double-peaked shapes, the shallow central valleys at moderate inclinations, and the restrained equivalent widths when surface densities are low, matching those profile across epochs, while the radial velocity curve remains steady, indicates that internal disk asymmetries precess without torque from a massive third body, a consistency that erodes the need for an additional unseen mass. The comparative view therefore tightens the chain of inference in LB-1 rather than loosening it. Where earlier stages of analysis might have leaned on the elegance of a single luminous star plus a heavy dark partner, the tools that resolve the southern controversy, dense time series spectroscopy, spectral disentangling spectroastrometry, polarimetry, updated astrometry and disciplined disk modelling have now been applied to LB-1 and produce the same qualitative answer. Two luminous stars share the orbit, one broad-lined and fast with a thin disk, one narrow-lined and hot with helium-rich features, and their antiphased motion accounts for the velocities. The similarities between the cases are not accidental. They reflect common physics of mass transfer, spin-up disk formation, and stripping in hot binaries. The differences in period brightness or environment modulate details without overturning the central template. In that light, LB-1 fits into a family of systems where initial claims of massive non-accreting black holes yielded to more mundane but physically rich binaries once faint spectra were extracted and geometry constrained. The comparative analysis thus serves as a check on method and on inference, showing that when the same techniques are applied with the same care, they converge on a picture that is both simpler and better supported by the full ensemble of observations. Open questions draw a clear map for observations that move from the widest context to the most intimate layers of LB-1, and they begin with distance because every mass and radius downstream depends on how far the light has travelled. Improved astrometry that gathers more years of precise position measurements will tighten the parallax and reduce the broad wings of the distance probability. Crowding checks that model the point spread function against nearby stars and cross-matches to deeper surveys will guard against subtle blends that bias the centroid motion. With a narrower distance in hand, the luminosities of both components sharpen, and the primary's radius and mass step into a smaller range, which in turn squeezes the allowed space for the secondary's mass through the measured mass ratio. Alongside this anchor, a fresh sweep through extinction is needed. Three-dimensional dust maps that merge stellar colours with far-infrared emission can refine the reddening along the exact sightline, and spectroscopic measures of interstellar sodium and calcium can set an independent column density. Polarization of field stars near LB-1 can test whether unusual grains alter the extinction curve. A consensus among these methods will keep the bolometric corrections and the spectral energy distribution fits from drifting as models evolve. Spectroscopy remains the center of gravity for progress. A denser time series with higher resolution and higher signal will let disentangling recover weaker lines in the narrow hot spectrum, including features of nitrogen, carbon, and oxygen, whose relative depths fix the chemical ratios that trace the history of nuclear burning and mass loss. Ultraviolet observations from space where interstellar absorption is measured cleanly, and resonance lines of wind-sensitive ions lie will probe whether either star drives a wind strong enough to matter for angular momentum loss. Near-infrared lines from helium and hydrogen will add leverage on the temperature of the stripped star and on the density of the inner disk, closing a gap left by veiling in the visual. Throughout velocity, precision must be guarded by stable calibration sources and by templates broadened to match each component so that the mass ratio and any small eccentricity are limited by photons rather than by the instrument. The disk demands its own campaign. Nightly monitoring of the deep red hydrogen profile across seasons will track the slow precession of any one-armed density wave and test whether the V/R cycle drifts freely or shows a weak resonance with the orbit. Radiative transfer models that include a thin, nearly Keplerian disk gravity darkening of the star and a mild outflow can be tuned to reproduce the full shape of the emission, not only the peak separation, and thus fix the temperature and surface density as functions of radius. Spectrostrometry, which measures microarcsecond level shifts in the photocenter across the emission line, can nail the rotation sense and place the disk plane relative to the orbital motion. If the disk is slightly tilted, a slow nodding in the polarization angle may appear. Multiband polarimetry that follows this angle, and the total polarization through the emission cycle, will test for warps at the few degree level. Interferometry offers the chance to resolve the elongated disk directly for brighter states or with longer baselines. Even a marginal detection of elongation aligned with the polarization angle would close the loop between geometry scattering and rotation. Photometry remains the quiet sentinel that can nevertheless reveal small clues. Long uninterrupted light curves at millimagnitude precision can catch low-amplitude coherent pulsations in the primary, if they exist, which would place independent constraints on interior structure through astroseismology and thereby on radius and gravity. The same light curves can test for a subtle ellipsoidal signal at half the orbital period that would further narrow the inclination, or for shallow grazing eclipses that would anchor it decisively if present. So far, the steadiness argues against strong geometry effects, but deeper sensitivity at redder bands where the disk contributes could reveal changes associated with slow breathing of the outer disk. High-energy observations set limits that should be pushed. Deeper X-ray exposures timed to conjunctions can search for weak wind capture onto the stripped star or rare episodes of interaction between the wind and the outer disk. Radio observations with high sensitivity can set a floor on any non-thermal emission associated with shocks in the disk or at the boundary of truncation. A continued absence of detections will tighten accretion rate limits and further marginalize scenarios that require a compact object. Astrometry at exquisite precision could in time detect the tiny reflex motion of the primary's photocenter over the orbit. While challenging at this distance, a detection would deliver the inclination without relying on polarization or light curve arguments, and would then lock both masses absolutely when combined with the radial velocities and the mass ratio. Theoretical work should keep pace with data. Binary evolution models that include rotation mass transfer efficiencies that can vary with time angular momentum carried away by outflows and internal mixing driven by spin can be tailored to match the present masses period and chemical signatures. A successful track must reproduce the near-circular orbit of many tens of days, the fast rotation of the primary, the modest rotation of the secondary, the nitrogen enrichment and carbon depletion at the surface of the stripped star and the faintness of the secondary in the blue and visual bands. These models can then forecast the future, whether the helium star will end as a white dwarf or as a compact remnant after a faint explosion, whether the orbit will widen or shrink under winds, and whether the primary will slow as the disk carries angular momentum away. Such forecasts do not belong to the present narration, but they shape which present-day measurements matter most. Finally, a set of discipline checks should be repeated with each new dataset. Rebuild velocity curves from separate line lists to isolate the influence of veiling. Repeat disentangling with altered masks and continuum placements to ensure the narrow template and its velocities persist. Refit the disk profiles with updated radiative transfer that includes small temperature gradients and subtleties in hydrogen level populations. Cross-check the distance against both astrometry and photometry whenever new catalogue releases appear. Compare the polarization angle across bands to test for interstellar contamination. Examine windows around telluric bands for residuals that mimic lines. Each repetition is a guard against the easy slip from careful inference to assumption. In the present, the core picture remains steady. A rapidly rotating hot star with a thin truncated disk and a faint hot narrow-lined stripped helium star revolve on a near-circular orbit of many tens of days. Open questions reside in the fine print, the exact distances and bolometric corrections, the precise temperatures and gravities of both stars, the detailed chemical pattern of the secondary, the viscosity and feeding rate of the disk, the minute eccentricity that precision might reveal, and the absolute inclination that a future astrometric detection could hand over. Progress will come from steady accumulation rather than a single decisive test, and the observational path is drawn measure more finely across more wavelengths, with instruments that hold their calibration and let the ensemble narrow the parameters until the masses and radii sit within small margins. In that way, the calm-ordered scene in Gemini continues to yield its numbers without drama, moving the system from a curiosity framed by an extraordinary early claim to a textbook example of how a binary shaped by mass transfer presents itself when viewed with enough patience to hear both voices and to weigh their motions together.